The last class, we talked about Laplacian mechanism and how it can give us privacy just from a bound on the sensitivity of a function, right? So it's something broadly applicable. So now we only need to know the function doesn't vary too much when you add some, you change one coordinate, okay? And another way to think about it is if you fix a privacy parameter and the accuracy parameter, then the size of the data set that you require to satisfy these restrictions will depend on how sensitive your function is. Okay, so if your function is very sensitive and you want to maintain privacy, then you need much bigger data set. Okay. So what are we going to do today? What we are going to do today is first study some sort of meta properties of differential privacy. In particular, we'll look at post-processing, group privacy, and then start talking about other kinds of functions and mechanisms for getting privacy. Okay. All right, so let's get started. Okay. The first sort of meta property I want to talk about is post-processing. What does post-processing mean? Post-processing refers to basically, you have your database behind some wall and you interact with it. You ask some questions, get an answer, ask some question, get an answer, and do this many rounds. At the end of the day, you build something else. Okay, whether it is some kind of statistics or maybe some more fine-grained information about the original database, you build something else, right? But you're a middle person, in the sense that you yourself are going to be a curator for something else. And what if I'm going to allow interfaces with what I collect? What does this do to the overall privacy of the original database? Ideally, what we would want is that whatever you do afterwards should not affect my original privacy guarantee, right? That makes intuitive sense and seems intuitively desirable. And in fact, differential privacy does satisfy that guarantee. Okay. So no matter what you do with the query answers, you are not going to violate differential privacy once you have it. Okay, what do I mean? So let's say you have some mechanism, right, which is taking a database and giving some answer. It could be a collection of answers, so it doesn't matter. And let's say this is epsilon differentially private. Okay. And maybe there is some other function now from y to z. So this is like y, this is z. Okay. Draw the squares. Okay. So they don't have to be the same size, right? Okay. So you're post-processing the answer from M. And you're wondering what about this function that goes directly from the original database to Z. So then the function that you obtain from going from the original database directly to Z is also epsilon differentially private. Okay. Does the statement make sense? Whatever you do afterward, the composed function is epsilon differentially private as long as the first one is. Okay. All right, how do you prove this? Any suggestions? How can we verify such a statement? As I said, privacy is proof. Right? You cannot say you have privacy without actually showing that the statement holds. Yeah.
Proves the function inside.
Exactly, right? So let's say we have two neighboring databases, x comma x prime are two neighboring databases. And when we have so what does the differential privacy guarantee say? If you have two neighboring databases, then the chance that you give a particular answer is close under both, right? So we want to say that for every little z in this range, the probability that the combined function gives the output z is close to what it would be whether, instead of x, if you give x prime, right? And the suggestion was, if I want to compute this probability, one way to do it is to look at the values in here, which actually map to the specific output little z, right? So I can write this as summation over all y such that f of y equals z, and to hit z, you need to first map to a value from m to some value y, which maps to z. Right? That's the only way to get the final thing. And now you're good. I can use the differential privacy guarantee of m to say this is at most e to the epsilon times m of x prime equals y. Okay. And now you get e to the epsilon times you kind of reverse the calculation to say this is just the probability that the combined function equals. Okay. So you get this post-processing privacy for free just from the definition. All right. Any questions? Yeah.
You got e to the epsilon.
So this is because of the differential privacy of m. Right. So this is a specific value y. And we said that we're starting with the assumption that m is differentially private. And what does it mean? For any two neighboring databases, x and x prime, the probabilities are within multiplicative e to the epsilon. Right. So we're starting with that definition, and then just applying the definition. Right. And you can see that that's why the multiplicative guarantee is so nice, because if you have some additive error, this argument doesn't quite work. Okay. So you have to be more careful when you have additive things, but once we have this nice multiplicative error, you get post-processing in a very clean way without any deterioration in parameters. Okay. Any other questions about this part? All right, if there are no other questions about that, so that's one meta property. So any differentially private mechanism will also satisfy post-processing. The other one is called group privacy. Okay. So group privacy means, maybe I don't want privacy for a single user, but even if, k users are changed. Right? It could just be because maybe I'm an organization, I have multiple members of my organization in the data set, and I want to preserve the privacy of the entire organization. Right? So in other words, what if we have two databases, X and X prime, okay, that differ in at most k rows. So instead of earlier looking only at neighboring, meaning one row difference, now we are saying I'm changing k rows. K users' data has been changed. Okay. What can we say now? So if my original function, let's say I have something which is epsilon differentially private, how does this affect the answers when I have X and X prime, which have k rows apart? Any guesses, suggestions? The original guarantee only says that two neighboring databases, if you only change one row, the answers are kind of occurring with the same probability or approximately the same probability. If I change k rows, what can we potentially say? Yeah. Yeah, so it should, exactly, right? So you should expect it to kind of multiply for each user, right? And in fact, such a thing is true. So we can show that if I have two databases who differ in k rows, then kind of get the same guarantee as before, except with a k in the exponent. Okay, so for every user, you kind of pay something in the privacy, but at least it's quantifiable once again. And how could you prove this potentially? And yeah. Exactly. We're going to use a bunch of intermediary databases, which allow us to go from the first one to the other one with k rows apart, but each time just change one row. Okay. And I mean, such an argument occurs often enough that it has a name. It's not important for us, but if you see it ever in other places, especially in crypto or something, it's called the hybrid method. Okay. Hybrid because we're introducing this hybrid databases which kind of go from one to the other, right? So we have X, right? Let's say the first k rows are different. Maybe let me write it this way. So this is X prime. First k rows are different. Hybrid just means, let me define a sequence of databases where x0 is X and I change the first row to match with X prime now. And then let me call this X1. I change the second row and so on. Okay. So let xi equal X with I rows change. Match X prime. Okay. You're going one sort of changing one at a time. And the guarantee that we have from differential privacy is for every output y. For instance, between the first two, there's only one row different. So we can apply the usual differential privacy guarantee. Okay. And we can also do the same for the next two, because they also differ only in one row, right? So we can say the chance under M1, X1 is the same as the chance under X2 essentially. And so on and so forth. Okay. And if you change these inequalities, you just get what we wanted. X0 was X and XK was Y, so we're good. Okay. All right. Any questions about this? We'll revisit this group privacy later, but it's good to just have at least the basic one. Okay. And these are called meta properties because these are true for any mechanism just from the definition of differential privacy. But it's not specific to like Laplacian mechanism or in how you implement it. But just if you satisfy the differential privacy guarantee, then these things continue to hold. Okay. All right. Now, with this in hand, let's go back to designing ways to answer interesting queries, right? So we know how to answer a median question, like if you want to, if you're interested in the average, if you're interested in median or any sensitive function, we know how to answer those things with the differential privacy, right? Without introducing too much error, you would use Laplacian mechanism. Okay. But what if you have something else? Well, before doing something else, let's think of some other kind of sort of aggregate statistics that people are often interested in. Okay. One of the statistics that you might care about is a broad class of such things is counting queries. Okay, so imagine you have a database of health records or like some genomic data or something. And one kind of interaction you would like to know is, okay, what's the number of people in my database who have so-and-so properties? Who have age 55, maybe gender something else, and then the heart condition is something, diabetes is something, and so on, right? Or if you're looking at genetic data, you might ask, okay, how many people in my data set have this specific marker and these vital statistics or something. Okay. So what you're doing here is essentially counting, and I'm interested in how many user records match some criteria, right? So counting query is kind of a catch-all term for questions of the form. Tell me the number of users or records in the database that match, that have certain property, some property you are interested in. Okay. It could be simple, it could just depend on a single coordinate, or it could be something complicated, it could depend on many things and whatever you have. Okay. So if you have a counting query, how can I get, how can I answer these things differentially private? Well, given any such question, the first thing you should think about is, okay, what does Laplacian mechanism give us? Right? Because it's a pretty generic method. We can use it for any kind of function as long as the sensitivity is somewhat reasonable, right? So what's the sensitivity of a counting query? For any counting query, how bad can its sensitivity be? Any guesses? Yeah. It's definitely more sensitive than the sum of the average, but it's not too bad either, right? I want to say it's not too bad in the following sense. Imagine I'm counting the number of people, are actually master students versus undergrad in this class. Right? If I throw out one person, then the count can change by at most 1. Right? So any counting query actually has sensitivity at most 1. Right? So recall, if I have a function f, then the sensitivity of F was the max value, max difference between two neighboring dataset evaluations. Okay. It's if I throw out the data or change the data of a single patient in my entire database, the count can change by at most 1. Okay. So what does this mean? This means that for any counting query, we can get epsilon differential privacy by adding Laplacian noise with rate 1 over epsilon. Okay. Remember, we said that if I have a function which has sensitivity S, then if I add Laplacian noise with the variance parameter S over epsilon, then I get differential privacy. Right? This is just saying for any counting query, I just need to do this. Okay. I mean, if you think of epsilon as being like 0.01, then you're saying I need to add noise which is roughly like 100 or maybe something like 200, 300, but not too much. So if I have a huge database, then if the count is expected to be high, then you're fine. Okay. Any questions about this? Yeah.
Curious. So I know you said that counting is not too sensitive. What's an example of a function?
Let's say I'm interested in knowing, let's say majority voting, right? You have a database of yes and no votes, and you want to know who is the winner. Okay. And if it's equal, let's say the red party wins and there's red and blue, right? Now, if I change one person, the function can change from 0 to 1, right? So in that sense, the vote can change. A single person value can change the sign of the function and so on. Okay. And you can also imagine other functions which are sensitive. But at the end of the day, what you want to do is quantify, right? So this is saying that if you have a counting query, this is exactly what privacy guarantee have, and this is the amount of noise you need to have. Okay. Okay. All right. Next thing is all right. Let's put some two things together. What if I make, I'm not interested in a single counting query, but I'm actually interested in many counting queries. I want to know how many people in the database have, age above something, have a heart condition, how many people in the age 30 to 40 are smokers, and so on and so forth. I have many different questions. So what if we make K counting queries? Right? So in other words, I have my database and I want to count K functions. So my output is K numbers, K integers. Okay. And I want to release this data with differential privacy. How much noise should I add for this? Yeah. Just individual, separate. I'm asking K different questions, one after the other, or at the same time, it doesn't matter. They're not composing, they just separately be. Almost, right? Because now the sensitivity can actually be higher, right? Because the way we define sensitivity for, if I have a function like this, which has K values, then the sensitivity was I take two neighboring databases And I need to add up the differences possible along each coordinate. Right? I mean, the changing x and x prime could lead to some change in the first coordinate to the second coordinate and so on. And the way we define sensitivity for multi-output functions was you just add up the sensitivity along each coordinate. Okay. So in this definition, what is the sensitivity of counting queries if I k of them? Yeah. K, right? Just add up the things individually. If I change one person, each of these counts can change by at most one. So the total net change can be at most k. It could be smaller, but at least k is an upper bound. All right. So this means that adding Laplacian noise with k over epsilon variance gives us epsilon differential privacy again. Okay. All right. So we can handle single counting queries. We can handle multiple counting queries. We just need to increase the noise a little bit. Yeah.
The sensitivity can be as large as k. Doesn't that the value?
It could, it kind of also intuitively makes sense. Right? The more queries you make, the more information you're revealing about the data set, about the database. Right. So you cannot, protect against thousands of queries while maintaining the same accuracy, especially without increasing the data set size. Right? So there has to be this trade-off always. And we're exactly kind of pinpointing, okay, this is the trade-off you're going to have. Yeah.
All these examples, we're like looking at like ones and zeros, and like, but if we had a data set where they're like numerical values, like
Right.
when we feel like sensitivity, are we focused on the, I guess, like the actual value of it, or would it be like
Just the absolute value difference. So in this, the Laplacian mechanism will work as long as this is bounded. This gap is bounded. They need not be 1 and 0. For as a starting step, we are doing this, but they don't always have to do that. Okay, and we'll look at some generalizations later on. All right. Okay. So we can handle counting queries, and I mean that was kind of easy. And another sort of important example in practice, but also kind of solved by what we have is histogram queries. Okay. So histogram queries just mean, maybe, so just imagine, you have a database. Right? Each person is in one of k categories. Right? There are k possible categories. Again, this is pretty generic, and I want to just draw the histogram of all of these things. It could be, the categories could be, okay, what is one category is age between 1 and 10. And the other category is age between 10 and 20, 30 to 40, 40 to 50, 50 to 60. It's basically k is the number of bins that you're using in your histogram, right? So imagine you have a database. A histogram plots are something that you do often, right? So you would like to give access to the ability to draw histograms, but with some privacy guarantees. Okay. So what are you interested in? I want to go from here to some kind of bar chart, right? Like the histogram. Type 1 has so many users, type 2 has so many users, and maybe this is the number of users of type 3. This is the number of users of type k. Okay. We want to go from here to some kind of diagram like this. And I'm using the type broadly. It could just be the number of bins that you have in your histogram class. All right. So we can think of a histogram query as a function from the database to k integers, right? It's telling me how many people are there of type 1, how many people are there of type 2, and so on. All right. So as a function, what is the sensitivity of a histogram query? Any suggestions, like how bad is the sensitivity of histogram query? Yeah.
And like if you change one age to another, you would have a sensitivity of 2
Mhm.
because you would change 2 categories.
Right.
But if you can also change like an age, but still having the same category, therefore having a sensitivity.
Right. So as an upper bound, it's at most 2, right? Remember, sensitivity is kind of worst case, right? What's the worst possible change in the outcome of the function? Okay. So here, the sensitivity would be at most 2 because, maybe your person was here. I throw that person out and bring a new person. Maybe that person, the new person, belongs somewhere here. Okay, so I'm decreasing this count by 1. So there's an error of 1 in this coordinate, and there's an error of 1 in this coordinate. Okay. So this is kind of, a case where, if you think of it as a function, in each coordinate, when you change the database, the error can be 1. But the overall sensitivity is only 2 and not increasing with k. Right? You can think of histogram also as like, individual counting queries. Okay, tell me how many people are there of type 1, how many people are there of type 2, and so on. Right? But the sensitivity is only 2 and not k because it's a disjoint. Right? The bins are never sort of overlapping. Okay. So almost it's kind of equivalent, but except in counting queries, the answers to the first counting query and the second counting query, they don't have any structure in them. Right? Whereas histogram comes under the assumption that the answers to the first counting query and the second counting query are kind of disjoint. They correspond to distinct people, right? So that's why when I change a single coordinate, I can only touch at most 2 bins. Right? Whereas if it's a counting, there's no connection between these different things, I could touch everything. So histograms are kind of less sensitive than just k counting queries put together, even though they look like it, just because of this additional disjointness structure. Okay. And so in particular, this means that for histograms, we can add much better noise, adding Laplacian noise with 2 over epsilon gives us epsilon differential privacy for histograms. Okay. Any question? Yeah.
So for this type of problems, what's the most people like general like is Laplacian or
For many of them, Laplacian is pretty good, but for some things, as we'll see, it might not be the best.
I want to query for max mean.
Yeah, we'll talk about that in a second. Yeah. Yeah, it's a very good question. That's where we are going to next. Okay. All right. So for this works well for histogram queries and so on. Now, okay. So let's try and think of other kinds of queries that you might have to answer. Right. So let's say the query I'm interested in is what was suggested. Sometimes I'm not interested in the entire histogram, but I would like to know, okay, what is the category with the maximum number of people? Like basically, you're asking what's the max height among anything here, right? And as an example, let's say you have something like you have a database of names. Right, you have a database of names and you have the US census data, let's say, and you want to know what are the top 10, maybe top 100 most common names. Yes, I want to know what are the top 100 most common names. Okay. What is one way to do such a thing? Any suggestions? Yeah.
So I'm trying to understand the problem. Do we care about the ordering? within the problem? Or just-
Let's say we also care about the order, top 1, top 2, top 3, and so on. Yeah.
Does it matter if it's ethical or not?
It's what?
Does it matter if it's ethical or not?
Ethical. Well, not right now.
It's like, if it's like ethical or unethical, then definitely one way is to just like violate the privacy and just get all.
Right. But you want to, so you are the US Census Bureau, you're trying to allow people to interact with the database this way while maintaining privacy. Right. So you want to say that, okay, anybody can query, okay, what are the top 100 names within the state of California, within the state of, maybe Washington, or within Southern California, within Northern California, and all of these things by the zip code even, but still maintain some kind of privacy as quantified by differential privacy.
Yes, but to me, it feels like the sensitivity of including one person in the database is still good.
Exactly, right?
You could just swap the order of.
Right. So when you change one person or kick one person out, the top 100, the counts are not going to change that much, right? So maybe one category which was in the top 100 now becomes like the 101s, the 101st, and it's no longer featured in the list, but the counts of the two have to be close anyway, right? If the difference was big, changing one person is not going to change who was the top 100, right? So the sensitivity is still fine. Okay, the sensitivity is still small. Okay, so that part is not affecting us. All right. But what, so the sensitivity is still small, so this implies that Laplacian noise with Laplacian mechanism. Actually, let me write it in the right way. Adding Laplacian over epsilon is still fine. Okay, still fine in terms of differential privacy. Okay, but as I said at the beginning, and I said several times, getting privacy is one thing, but we should also check how it hurts or affects the accuracy. Okay, for counting queries and so on, for average, for instance, it was reasonably easy to quantify how adding the noise was affecting our accuracy. right? Because you just added something. So you know exactly what the error you're introducing is, and that told you, okay, what's the chance that you're off by so much and so on. Okay. But for the max, it seems like a more cumbersome or more complicated function. Right? So how can we quantify how is it affecting our accuracy? Right? So let's think of that. Okay, so adding Laplacian noise to our epsilon just means that so the suggested process is, you have your database. Okay, you compute the counts of the top 100 maybe let me draw that in order. Okay, count, I compute these frequencies of top 100. And then I add some Laplacian noise on top, right? Add some noise. Okay. So this is the Laplacian 2/epsilon. Okay. So you can still quantify the amount of error you get, right? So because we know that if I add Laplacian, if Z is my noise variable, it's being drawn with this noise, let me write it actually, then right, so we have this kind of these are called tail bounds, meaning they quantify how fast is your probability decaying in the tails, right? So in particular, we can say, okay, what's the chance that the noise is more than e to the minus, 10? Sorry, what's the chance that the noise is bigger than maybe t times 2/epsilon? That chance is at most e to the minus. Okay. So we know exactly how much noise we are adding and how much, what's the chance it is bigger than some magnitude. Okay, using this, we can get some reasonable estimate of how our answers change. Right? So this seems fine, for answering things like what are the top 100 most common. Okay. Now let me change the question a little bit and then see what happens. So sometimes what we are interested in is not just some numerical fact about the database. Sometimes we might be interested in something which is non-numeric. Okay, what do I mean? Question. Now you have a huge database of medical records, and you ask, I have a database of medical records, right? And let's say medical records of maybe cancer patients, right? Or something like that, something sensitive. And you ask, what is the most common form of cancer? So I'm not interested in the count as much as the label of the type which is most common. Okay. Right. So it's not a numeric data. I want the answer to be something like, okay, it is breast cancer. It is, maybe pancreatic cancer and something like that. Okay. Yeah.
How would you define the distance?
This is sorry.
Calculate the sensitivity. How do you define the distance?
Exactly, right? So it's not clear that you could, I mean, it's not really talking about, you can't talk about sensitivity here, right? Because it's a categorical data that you're outputting, right? You can't say, between red, blue, and green, how do you compare sensitivity? If what you're outputting is not a number, what does it mean to say something is sensitive? But you can easily imagine situations where you have to answer questions like this, right? So, what are some approaches to handle such? Any suggestions?
I know this is a bad suggestion, but just to get it started, we try to impose some canonical ordering on it, but then like you assign a number. Of course, that would imply like some sort of numeric relationship.
Right. But I think that's something to get started, right? So I think that's a reasonably valid suggestion. And in fact, in many cases, that's what happens even in modern ML systems. Like if you have dog, cat, and so on, these are the labels that you're interested in, but you do something called one-shot encoding or one-hot encoding, where essentially you are mapping everything to some numeric value, right? Like dog will be number 1, cat will be number 2, and so on. Okay. So the first suggestion is, create or assign a number to each category. Okay. So meaning if we have k types, then our answer is going to be something from the database to a number from 1 through k. Okay. This is pretty good, but what happens to the sensitivity? What is the sensitivity now? Yeah, it'll be k. Right, so the sensitivity is k minus 1, but you can, let me just ignore the minus 1, doesn't matter. Okay? The sensitivity is at most k. Okay, so meaning we need to add Laplacian noise with k over epsilon. Now, when we add so much noise, you can imagine the accuracy is going to take a big hit. Yeah. Mm-hmm. Right, but the problem is you want your privacy guarantee or sensitivity condition that should hold for any databases, right? So you should also work when you don't have that prior information that you're assuming, right? So if you had the prior information, you could probably use it, but if you don't have it, then you'll end up in the same scenario, right? Yeah.
Instead of having the output set to be like after like a kid.
No, it registers sensitivity per coordinate. But remember, when you talk about Laplacian mechanism, the sensitivity adds up across coordinates, right? But you're on the right track, and that seems like it seems like an overkill. Maybe there's a better embedding or encoding of the categories so as to exploit it and so on, right? But even before that, let's see what we want really, right? We want differential privacy, that's for sure. But also we want to preserve accuracy in some sense. So what does it mean to preserve the accuracy, right? So preserving accuracy means what? So the accuracy would mean something like so what would be a very desirable accuracy, right? You're answering something which is categorical. You can't just say my value is actually close numerically to the true answer. That doesn't make sense, right? Because these labels 1 through k are completely arbitrary. Okay, so if you want to quantify accuracy in some way for this, what would be a reasonable thing? Yeah, that's too hard, right? Because by definition of differential privacy, you will lose something. So what would be something in between? Well, you can say maybe I'm not outputting the actual max, but whatever I output is close to being the max. Okay, maybe I don't output whatever is the highest value, but what I output is maybe very close to being the max. That is somewhat okay. That's the price, at least I'm willing, seems reasonable to pay if I want privacy. So the max at a count of 100, what I'm outputting has a count between 100 and 98. If I can do something like this and I get privacy, I should be more happy than saying, okay, my count can be anywhere between 100 and 0. Right? Okay. So maybe one nice notion of accuracy to aim for is answer has value that is close to the max. Not answer, but okay, let me write it more precisely. I want to say count of what we output is close to the count of what count of the max. Okay. Yeah.
Be like a parameter of one of our outputs.
Exactly, right? You can say, it's basically like fixing the privacy, the accuracy, and then you check, what is the data set size I need or something like that, right? So going along that direction to quantify how this affects your privacy. Okay. Excuse me. And if you want to do something like this, as it turns out, there is actually a simpler thing that you can do, which still preserves privacy. It's more non-trivial to analyze, but let me just state it, and we'll look at a more general thing. Okay. And this is called noisy max algorithm. It's very simple. It just says, imagine I have a function. Okay, I'm starting with some function, and what I want to output is my function has k outputs, but what I am really interested in is which coordinate has the maximum value. Can imagine my function counts, what is the frequency of each type of cancer, right? And what I'm interested in is which is the maximum value. Okay, going from numerical to categorical. Okay, does the question make sense? I have some function I'm interested in, okay, what is the coordinate which maximizes this function across the k values? And this is more general potentially than the cancer question that we were asking. What is the most frequent one? You could potentially compute everything and then compute the max. Okay. So the noisy max mechanism is something like this. It says add noise, which is Laplacian 1 over epsilon to each coordinate. Okay. So suppose f as sensitivity 1 along each coordinate. Okay. Imagine each coordinate is counting something, right? You know, it's counting. Okay, let's see. Is each coordinate of f counts frequency of type I, meaning how many users are of type I and so on, right? You're counting for each coordinate, how many users have that type. You add Laplacian as 1 over epsilon to each coordinate, okay? And then you compute the max of these noisy counts. Okay. And then you release the ID. Disease. Right. So I first compute, you know, how many people have this specific type, you know, how many people have this specific type and so on. I add noise to each one separately and compute the max of the noisy counts and then release the ID of the max. Okay. So you're essentially doing some kind of perturbation. You're computing the counts, perturbing them, and just running the max in the perturbed counts. As an algorithm, it makes intuitive sense. I'm just saying I'm adding noise to each count and then compute the max and hoping that that's kind of good. So what do you think? Is this a good mechanism to try? Would this preserve differential privacy? Any guesses? Yeah.
My guess is that it would. Perhaps it would hurt them.
No, it's actually much better in accuracy than the previous one because you're adding much less noise, right? Way less noise. You don't have the K anymore. So it's not growing with K at all. The noise is not growing with how many categories that you have. Okay. Yeah.
Not sure if I understand it correctly, but we're recomputing the noise. Able to. There's a lot of information.
No, but we are only answering one max query, right? But this is what the curator is doing. It computes a count for every type of cancer, adds the noise, and releases the ID of the max with this noisy counts.
On different queries.
It's the same mechanism. Like if I have two neighboring databases, then it's going to do add the noisy things to each one and then release the ID of the max. Okay, it's actually a little bit delicate to prove it. You cannot use sensitivity analysis anymore because the function that you're releasing is some weird function. You're releasing the ID of something, right? So that's not the same as just adding. I can't bound the sensitivity of this and use standard analysis, okay, because the sensitivity is pretty high, as we saw. Okay, but as it turns out, this mechanism actually has much better privacy guarantee than you would get from just using the sensitivity analysis. Right, this is just to say, if you have a bound on the sensitivity, you do get some privacy. But even for functions which are sensitive, sometimes you can do better if you do a better analysis. Okay. Yeah.
I'm just
confused, because saw an example where choose the 100 most common names. What if we change that to like choose the 2 most common names? And we showed that can be differential private with adding, I guess effectively adding.
Okay, so maybe I should have been more precise here. I should say, what are the counts?
Oh, you're okay. So you're actually
Like, you here you're really interested in the counts, right?
okay.
Right, but here I'm interested in the ID, like I'm not so much,
But you can add less names.
yeah, exactly, right? So, okay, so I mean, in fact, you can add even less noise. The noisy max mechanism, as we defined it, okay, is known to be epsilon differentially private. Okay, this doesn't follow from what we did, because the sensitivity of the function that we're computing is like k. When I change one user, the max can shift from 1 to somewhere else, right? The sensitivity is k, but the privacy is much better. Okay, sensitivity is just one way to control privacy. Sometimes you can do better. And the proof of this is somewhat involved. We are not going to do it. But there's a textbook by Dwork and Roth, and I'll put a reference to it from the textbook. Okay, but what we're going to do is something much more general than noisy max. We'll try and solve such a question. I have some function, but what I'm interested in releasing is kind of the maximizing coordinate or something like that of the function. Okay. So noisy max, again, just to summarize, noisy max sensitivity is bad for the max function, but noisy max actually has better guarantee. Meaning you need to add less noise than you would presume to require just from the sensitivity bound. Okay. So, so let's take a 5-minute break, and when we come back, we'll basically solve a more general problem than noisy max using an important mechanism called exponential mechanism. Okay, so Laplacian mechanism, now we'll see exponential mechanism, which generalizes the noisy max setting to, kind of related functions. Okay, let's take a 5-minute break and then come back. Okay. So let's look at another category of functions which kind of are worthy of study because they occur often enough and they're helpful as subroutines in various other things. Okay, so Laplacian mechanism is good because it applies broadly to sensitive functions, right? And we just saw an example where that's not the best thing you can do. Like for computing the max, if you just apply Laplacian mechanism and sensitivity, you don't get the right answer. So what else can we do? Okay, there's in fact a, I think a broad category where you should be able to do better. And an example of that, let's look at something called digital goods auction, right? So let's say, I create a nice painting, make a NFT out of it or whatever, and try to sell it. Okay, I'm putting up this painting for auction. Okay, I'm putting up the painting for auction, and the way the auction is going to go is user 1 says, okay, I'm willing to pay $1. User 2 says they're willing to pay $1. User 3 is willing to pay $1, let's say, and user 4 is willing to pay maybe 3.01, or let's say, yeah, something like this. Okay, and based on this, I can set the price. So I see the prices, and sorry, I see the bids, and now I have to set the price so that I maximize my revenue. Okay. So these are digital things, I say, okay, I can, meaning they can be replicated. It's not a single copy, there are many copies, you can send them out, but I need to set the price uniformly. Okay. So if I set price to be $1, how much revenue do I get? Revenue is 4 because everyone will buy it, right? Whereas if I set the price to be, let's say 4, how much revenue do I get? 0. If I set the price to be 3, how much revenue do I get? 3. Right? So in some sense, like setting the price to be 1 seems to be giving me the best revenue, right? Not the highest, but kind of, that good. And if I set the price to be 3.01, how much revenue do I get? 0, right? So as a curator, the function that you're interested in is, I can say revenue at price B, right? Is how much revenue I get if price is set to P. Okay. And what I'm interested in is what is the value or what's the price that maximizes my revenue? Okay. So the input are this set of prices, this set of bids, and I need to set a price to maximize my revenue. A little bit like the noisy max that we saw, right? Now you're not just interested in a numerical value, but you're interested in the argument that maximizes a function. Okay. So now imagine you want to run such an auction in a differentially private way, right? You want to say, okay, I can collect bids from everybody, and then when I release the thing, I still get some privacy guarantee. Okay. And even from this example, you can see that the function seems, it can be even small changes in P could result in big changes in revenue, right? So whether the price is 3.01 or 3, the change in the revenue is huge. If a small change in the price, the change in the revenue can be very big because it's sort of this threshold phenomenon, right? So what can we do for such functions? How can I compute such things differentially privately? Is it possible? What's the best you can do? Okay. To understand this, let's introduce a kind of abstraction of such tasks. And I'll say we have some range R. Okay, let me actually say P. We have some set of allowed prices, okay? And we have a utility function. Think of it as some kind of revenue function, the function which takes my database and a value in P and gives me a real number, right? So it takes me a set of bits, a price, and tells me how much revenue you would get. So for instance, here, if the price was set to be 2, how much revenue would I get? 2, right? So that's the function that you're computing. Okay. So u of x comma p, think of it as the utility at price p. Okay, that's just our kind of mental interpretation. And what is our goal? Our goal is to compute or release our goal is to compute or release the value p which maximizes this utility. Right? Kind of a seemingly substantial generalization of the noisy max. Right? So first example, clearly digital goods auction fits the above. Right? We just saw an example. The utility is just the revenue that you would get. Okay. And how about computing the max? Would that also fit this category? If so, what should your utility function be? Any guesses? Well, I can say if I have k types, right? I can define a function which just takes x and id and tells me count of how many items in x are of type. Okay. Then computing the max or argument of the max is just computing, whichever ID maximizes this counts. Okay. This is just saying that, we are in fact generalizing the earlier question potentially to something much bigger. Okay. All right. So for such functions, the Laplacian mechanism is not actually the right one, but there's something called the exponential mechanism, which turns out to be much better. And this was introduced by Mekshari and Talwar in 2010. And what they suggested was the following. Given utility function as above, they said what you should output is the following. They said, okay, we want to compute the argument of the max, but instead of computing the max coordinate, what I'm going to do is output each coordinate with some probability so that the max one will have the highest probability of going, right? So imagine, on each person here, there is some kind of score, like, 1, 2, 10, 100, and so on, right? And my goal is to output the person with the highest score, the ID of the person with the highest score. I can just compute the max and output that. In the exponential mechanism, the basic idea is, okay, let's output each person's ID as the answer with some probability, which is kind of proportional or grows with their score. The max person will have the highest probability, and it kind of degrades from there. How does it degrade? It degrades exponential. Okay, that's why it's called the exponential mechanism. And it's proportional to x of epsilon times u of x comma p. Okay, it's a very concrete sort of formula. It's saying you have to output IDP with probability proportional to exponential in epsilon times u of x comma p. Okay, divided by this delta u. Let me just tell you what this delta u is. This delta u is basically the analog of sensitivity. Okay, you're still scaling things down by some kind of sensitivity. For two prizes and for two neighboring databases. What's the maximum difference that I can see between the utilities? Okay, you had a question?
That's what the delta.
Yeah. So delta U is measuring, it's kind of like the sensitivity, but it's not checking the sensitivity of the max function, but how much does the utility change when I fix the price, but change the database? Okay. So for all possible prices and over all neighboring databases, what's the difference between the two values? Okay, you're not, the important thing is kind of you're looking at the same price for comparing the two databases. Okay, that's this definition of delta U, which is some form of sensitivity. It's not like the sensitivity that we saw earlier. It's a little bit weaker, but that turns out to be enough. Okay, but the algorithm makes sense. Yeah. So delta U, you should think of it as some kind of scaling, right? You know, if your revenue suddenly went from 100 to 0 when I change a single user, that means that you cannot do, you cannot differentiate between scores that much. Okay.
Kind of like softmax.
It's exactly like softmax, right? It's really like softmax, and this delta U controls, how much importance you give to the highest coordinate. Okay. If delta U is very big, then you're kind of scaling down the differences, right? If it's small, then you're kind of scaling up the differences. Okay. Any questions? Okay. So that's the exponential mechanism. It's a very concrete mechanism, as I said. And what do we know about it? So the claim that they showed is that ME is 2 epsilon differentially private. Okay, so it is a differentially private mechanism with 2 epsilon. I mean, I'm doing this 2 epsilon here instead of epsilon because that's the way it's usually defined historically. So let's just stick to that. Okay. As an example, let's think of let's say we're trying to apply exponential mechanism to computing most common form of cancer. Okay. So if I'm trying to do this, you have a database and then you have types of cancer, and then the answer is going to be, what is the count of the number of people with this type of cancer in your database, right? So U of X comma ID is number of people with type ID. Okay. So if this is the way, then what is delta U? What's an upper bound on delta U? When I change one person for any ID, how much can the count change? Most one, right? So delta U is actually less than or equal to 1. Okay. Because you're only looking at the change in the utility and not in the actual max. Right? Earlier, when we said you define the function as a max, the sensitivity was terrible because you can flip from one coordinate to the other. But here you're only quantifying it in terms of the change in the actual utility. Okay. So that means that, so what would you do then? You would say output, I with probability proportional to X of epsilon times U of X. Okay. That's what exponential mechanism becomes in this case. All right. So let's just sort of belabor this point a little bit. What does it mean to output something with probability proportional to this exponential U of X comma I, right? So it means that, you have to first normalize all of these numbers so they add up to 1 and just scale that down, right? So meaning, what am I going to do? I'm going to say, output I with probability X of U of X comma epsilon times U of X comma I divided by the sum. Okay. So you're outputting each I with this probability. So if one person has a count of 1 and another person has a count of 100, the person with the count of 100 has like a huge probability compared to the person with count of 1. Right? Because you're going to get hit with this thing in the exponent. Right? And as you said, it's really doing softmax instead of actually computing the max. All right. Okay. So that's the example, for a noisy max kind of setting. But let's try and prove, why is ME differentially private? Okay. So why is the exponential mechanism differentially private? Yes, if you want to show differential privacy, you just start with like 2 neighboring databases, check the probabilities, and then just do the calculations from there on, right? So take 2 neighboring databases. X and X prime. Okay. And what's the probability that, maybe under ME, I output P versus what's the probability that under X prime, I output P. And these are the 2 things that I'm interested in. Okay. So in particular, I'm interested in the ratio of these two things. Well, actually, let me maybe write them down separately so that okay. So choosing things with probability proportional to the exponent just means that you take the exponent and normalize by the sum. Okay. And the same thing for x prime. Right. And the proof is really just sort of writing down these expressions and computing the ratio. Okay. We have these two equations, and by definition, we know that how much can these two differ? They can differ at most by delta U, right? That's how we define the sensitivity. For any delta U was a max difference in these values, right? So this is at most delta U. Okay. In particular, when I take the ratio of these things, I just get 1, right? Okay. So we have like a numerator, denominator, and denominator. So we'll compare both of them. Like we'll compare the numerator to numerator and the denominator to. So let's do numerators. So we have epsilon, exponent of this guy. Because the gap, the ratio of the gap is at most 1 is exactly okay. So this is at most e to the epsilon. Okay, because the gap is at most delta U, so the ratio is at most 1, and you get e to the epsilon. This is for the numerators. And for the denominators, what can we say? We have okay. With the same argument, I can write this as at least okay. Because term by term, when I take the difference between the two things, the gap is at most 1. Right? So the denominators, the ratio is also good. So applies. Nice. Okay. And if you put these two things together, you get so we compare the numerator to numerator, the ratio is at most e to the epsilon, the denominator to denominator, the ratio is at most e to the epsilon. So I get probability that ME of X equals P divided by ME of X prime equals P is less than or equal to okay. So the exponential mechanism does indeed give us differential privacy. All right. Any questions about this?
I'm confused about the denominator quality.
Mhm.
Um,
So for denominator, what we are doing is basically comparing term by term. So just think of fixing a single Q, right? Maybe let me write it down here. Oh, actually, I think I can write it down here. So X of epsilon times U of X comma Q right is at least it's really this inequality, but in reverse, right? If you think it, okay, that doesn't make sense. It's just the same inequality, but it should also go in the other direction. Okay.
Same inequality as in the mirror.
Exactly. We're using it, yeah. Yeah, precisely. You know, using it for each term, but then you're adding things up, so everything works out fine. Okay. All right. So that's Laplacian exponential mechanism. It does give, you know, epsilon differential privacy, but why is it actually, you know, is it better than the true thing? You know, how can you quantify the accuracy? Well, as I said, you should compare the utility or the accuracy in terms of how close is the value that you get. If you're running a digital goods auction, right, and someone says, okay, you can get privacy, but the net revenue you're getting is way off from the optimal revenue, that's not a good mechanism. Right? No one would take it, for example, right? So the question to ask is, if, you know, instead of running a pure auction, I run a private auction using exponential mechanism, how much, you know, what is the chance that I lose X amount of revenue? Okay. So can we quantify that? And it turns out we can actually quantify that exactly. We can quantify it as follows. Okay. So the revenue or the utility that you get from running. So the exponential mechanism is outputting some, you know, price point or some ID, right? What's the utility that you get out of that? You know, utility you get by using ME. You know, if it's way off from the optimal, it's not a good thing for us, right? So the chance that it is very far from the optimal utility, which is the best possible utility. The best possible revenue, the chance that we are way off from that can be quantified exactly. It can be quantified as follows. It's minus so maybe actually, let me write it differently. I think that might make sense. No, let me keep both. Okay. This is saying, let's say I'm interested in the chance that I'm far from a utility, and I'm interested in the chance of failure being something like, 0.1. Then it can tell me exactly how far I'm going to be. Okay. So another way to write down the same equation is so one way to interpret this is like, it's kind of like it's likely that you will lose some utility, but how much you lose is kind of logarithmic in the number of options that you have. Okay. So if the number of categories that you have is, like 100, then how much utility or how much revenue you're losing is like ln 100. Okay. So if I have 1,000 users bidding, then the amount of revenue I lose is something like ln 1,000 divided by the privacy parameter and the actual sensitivity of it. Okay. So approximately. So what you get is going to be roughly at least this much, and the chance that you even go lower is going to kind of decay from here. Okay. So as an example, for noisy max, what was the P? That will be the number of types you have, right? So it's just like K, and delta U was 1, right? So it's saying the count or the utility that you get from running exponential mechanism is roughly ln K over epsilon. Okay. If you have 10 different kinds of cancer, you're pretty close to the optimum. You're not that far. Okay. So this logarithmic dependence on the number of types is what makes exponential mechanism better. To just use plain noisy, plain sensitivity bound Laplacian mechanism, you can get privacy, but then what happens is the utility you get will have a factor that is linear in the domain size instead of being logarithmic. Okay, and obviously logarithmic is much more desired, right? And so that's one reason why exponential mechanism gets used a lot, because of this logarithmic dependence, right? Okay, so let me stop with that here, and in the next lecture we'll talk about other properties of exponential mechanism and what are the variants of privacy we can look at. Okay, all right. Not quite. You'll actually prove it in the assignment. I'll give some hints in the next lecture and you'll prove it in the assignment.